Today we're going to be discussing the sum of a geometric sequence, and that's our last section of the chapter. Let's get started. For our formula, when we're finding the sum of the first n terms, our sigma notation here means we're going to be taking all the terms for a geometric sequence and adding them together. So the actual formula here is a sub 1 times 1 minus r to the n over 1 minus r. What that means is we need to know three different variables. We need to know what the first term is, we need to know what the common ratio is, and how many terms we are adding together. For our first example, we have our sequence below here: 5, 10, 20, 40, 80, 160, 320, and 640. So we could simply add all those terms together, but we're going to go ahead and use our formula to verify that it works correctly. To begin with, we want to identify our three variables: a1, n, and r. a1 is 5, n is 8 because we have 8 terms, and then our common ratio we find by dividing any two consecutive terms. In this case, I divided the second term by the first term to get that r value is 2. So, for our formula, I'm going to plug in those three variables, and I have 5 times 1 minus 2 to the 8th over 1 minus 2. When you simplify everything and we get to our final answer, you see that the sum is 1,275. One thing I would like to comment on here is, if you're having trouble getting this answer, I would suggest that you do your numerator first, then your denominator, and divide the two, and lastly multiply by a1. So do your sum in steps. For our next example, I would like to see if you guys could apply the formula. So we want to find the sum for 20 terms, and we have the sequence 1, 3, 9, and 27. So remember, you need to find three things: find the first term, find the common ratio, and identify how many terms are being added together, and then plug them into your formula. Go ahead and do that now, and give me your answer. We don't always have the sequence in front of us to identify our three variables, a1, n, and r. Sometimes we have our geometric formula instead. So we're going to look at our expression here, and we can see that we have, for sigma notation, n equaling 1 to 12, for the formula 4 times 0.3 to the n. So we're going to start by identifying our first term. To find a sub 1, we would simply take our 1 and plug it in for n, and we would get 4 times 0.3. To find r, we will look at the number being raised to the exponent. So in this case, 0.3 is our common ratio. And finally, to find n, the number of terms we're adding together, we look at our top value here, and it shows that we're going to be adding 12 numbers together. So when I go to plug in my three variables, a1, r, and n, again I'm pulling them from the formula here, and I get 4 times 0.3 times 1 minus 0.3 to the 12th over 1 minus 0.3. So again, just to recap, our number being raised to the exponent, the 0.3 is our r value. The first term is found by taking this expression and raising it to the first power, and then n is found by identifying the number at the top of your sigma notation. So when we go ahead and calculate our sum, we get 1.714 as a sum of the first 12 terms. Alright, now it's your turn. Looking at our notation here, the formula, we have 2 to the n minus 1 for n equaling 1 to 9. I'd like for you guys to go ahead and identify the three variables and then tell me what the sum for our geometric sequence is. Occasionally, we have an infinite geometric sequence, and it's called a geometric series. The sum for a geometric series has a different formula. It is a sub 1 divided by 1 minus r. So again, this part is our formula. This part is telling us to add up all the terms for that expression. We know it's infinite because if you look at our sigma notation, we have an infinity sign at the very top. So again, what that means is our terms just keep going and going and they never stop. If our r value, the common ratio, has an absolute value that is less than 1, then we have an actual sum. If our r value, our common ratio, has an absolute value that is 1 or bigger, then we do not have a sum. So when you're trying to evaluate an infinite series, you want to first identify the common ratio to determine if you even have a sum. If you do, if your r value is less than 1, then you would apply your formula. Let's look at two examples. For our first example, again, we're going to try and identify what kind of infinite series we have. To begin with, we know it's infinite because we have an infinity sign above our sigma notation. We then want to identify the common ratio. In this case, the common ratio is 1/2. Since the absolute value of r is less than 1, you're going to have a sum. And the reason why we have a sum is because as you multiply a small number to a bigger exponent, it gets closer and closer to 0. So eventually, it's like we're just adding 0 at the end of our series. So to find our sum, we're going to find a1, which we can do by plugging in a 0 into n. And the reason we're doing 0 is because that's where index starts. If it started at 1, we plug in a 1, but since it starts at 0, we plug in a 0. So our first term then is going to be 1/2 to the 0 power. And then we're going to divide that by 1 minus 1/2 because that's our r value. When you simplify this, you get your answer of 2. So our infinite series has a sum of 2. For our last example here, we're looking again at an infinite series, and we know that it's infinite because again we have the infinity sign. So I'm going to identify my ratio, which in this case is -3/2, and the absolute value of -3/2 is bigger than 1. This means that our terms are always going to be getting bigger, either positive or negative, and so we're never going to have a convergent sum. We would then say that there is no sum for this, or there's just no solution. That concludes our notes for today. We're going to go ahead and apply this in class tomorrow, so make sure you're ready to do that.